Yes, hello everybody, my name is Felix, and I'm a little famous for my WebGL presentations. I had this presentation before at the FMX conference in Stuttgart 2 years ago, and I've heard earlier this year from Chaos Cologne, and I thought, well, that's my place, I should do this again. I have actually not very much new stuff since then, but I will show you some of my procedural generated content. I have actually no idea what I was trying to say with this when I was writing it down 2 or 3 days ago. Maybe I'm just nervous, but I skip over this. Just tell a little bit about myself. I learned programming early as a teenager. I've a dad who's also a computer programmer, and I was introduced to low title graphics as maybe when I was 12 or 13. When we learned JavaScript, I would rather say HTML in computer science class at school. I soaked it all up in 2 weeks, and then I discovered there was JavaScript. At this time, there was Internet Explorer 4 that didn't even have the document object model, and I was celebrating the day when the Internet Explorer 5 was released. So then, around 2000, I switched to the server side as well, programmed my first web pages, and had a guest book on my site, which I programmed in JavaScript and in Perl. So then there was Milkdrop. Milkdrop is a music visualization plugin for Winamp, and I will come to it closer. I think I discovered it in 2003, and in 2005 I thought I could release my first preset pack, and then in 2008 customizable shader programs were introduced. You may know or you may not know that there are several shader toys on the web now, and I think I have it all through many years earlier. I've studied computer science at the university where I was doing the software engineering branch and object-oriented systems. I learned to program in Java and C# and the whole modeling bandwidth. So Milkdrop is very, very, very basic. You have simple shapes that you can animate with a little scripting language, and you can transform the backdrop with a warp feedback. So you can place some colors and then let them flow. That's what I was resembling with my first takes in WebGL as well. So Milkdrop is an IDE. You can just start it up. Okay, nice. Oh, wait a second. I'm not sure if I have sound checked in by the display card. I'm a little confused. Oh, thank you. We can cut it off, right? Can I plug in sound somewhere here? So you started the mid-drop visualization and you can go full screen. There's a help, press F1 to see the help, but more interesting is the editor. You press N to open the editor and can directly jump and edit the program, the shaders. You can save them, and load them, and give them names, and by this I mean when you find the name Flexi in one of them, that's my name. I plugged in a stream to show you that it's actually really live music visualization. It's nothing pre-recorded or something like that. It's all generated on the fly. A good bunch of my presets is included with the official download since 2008. It was Winamp 5.5. But I'm actually not very much active anymore. You see, looking into the forum, but I didn't do anything new since 1 or 2 years. But that's the way I learned shader programming. So I started to reprogram my first mid-drop clone in Java and the processing language, but at the same time WebGL appeared and I left processing aside and programmed back in JavaScript, where I really learned programming as a teenager. So the most simple thing you can do with a texture feedback loop is a tunnel. And you see it's running in the browser and it's really fast. This one is 1 megapixel. This one is quite similar, but imagine you don't use just one camera to feed it back into the loop, but two. And you can move around them, scale and rotate both cameras, and you can have, with the feedback, a really responsive fractal generator. It's one of the lessons that I learned with mid-drop very early. And it was easy for me to adapt this to JavaScript and WebGL later. Actually, this one is not even with WebGL itself, but standard HTML5 canvas. And I won a prize with it last year. It's written in less than 1 kilobyte of JavaScript. So with WebGL, you're not limited to this linear thing, but you can also use more complicated, complex function. Complicated is wrong. The formula is really simple. In this one, I've placed 4 roots in the complex number plane. I can save one with a click and move it around. Last year at the 1 kilobyte combo contest, there was also a new category, the WebGL and the 2K variant, but I did wrong and I did 2K in WebGL, which was not allowed, and so this funny little guy was dismissed by the jury. But you see, I'm using heavily the edge enhancement filters. It's something you can do very cheap on the GPU side. And this one is a feedback system on 2 megapixels. There are obviously 3 color channels in a texture, red, green, blue. You don't see red, green, blue here. I've recolored them in the final composite step, where I've also applied the edge enhancement. So the basic setup is also very simple. There are mainly 2 shader programs. One shader program that uses the previous frame as an input for the next frame. That is the warp shader. And then you can render this warp feedback texture to the screen in the composite shader, and it does not get into the feedback loop, but you can layer different effects on top of each other and finally on the screen. What Milldrop also had was this grid-based texture warp, but I did not include this in my simple shader pipeline in WebGL. So what can you do? I'm actually not using any geometry in my experiments. This is a WebGL scene, which is, you could say it's ray traced. The whole image is spanned by 2 triangles. That's the idea behind every shader toy. This one was me taking a photograph of the cathedral when I arrived yesterday. So I hoped I could show you a feedback loop on the actual live stream, but I don't know if it's really streamed live. Is this a correct link? Yeah. Pity. Some points from this slide I've already mentioned. 2 triangles, yes. I didn't use any framework. I programmed this all by hand from top to bottom. So every page you see on this slide deck, you can simply grab the HTML file, take a copy, and break things. Just do it. I very much recommend it. Milldrop had blur textures pre-calculated, and they can be used for very surprising effects, very naturally looking effects. And in Milldrop itself, you have 3 different resolutions of the blur textures. I have extended this a little bit, and yes, you will see. Also, I've dropped the 8-bit textures for float 32s, which gives a lot of more opportunities also to use it as a simulation. But I'm not the only one who does this, and everyone who knows a little bit of WebGL knows 3JS. This is the most famous library and framework for productive WebGL works. And Stephen Wittens wrote a render-to-texture library for 3JS, and it does pretty much the same thing that I'm doing without 3JS. Then there are different clones of the original Milldrop. For example, there's Milkshake. Milkshake has SoundCloud integration. It's all open source, you can find it on GitHub, and there's a Python-based shader preset converter, so that you can take your original milk content and I don't know why it holds, but no. Butterchurn is even cooler. Butterchurn has a converter for the HLSL DirectX shader programs to GLSL WebGL shaders. And I was quite amused when I found the site, because the first scene in this was programmed by me. I didn't know about Butterchurn, but I really like when things like that happen. Every once in a while I discover YouTube videos of Milk with my content, and I'm just happy.
Yeah, please.
Why not? Okay. Any ideas what I could? You know. No. Something is not working properly here. That looks better. Okay. If we would hear something, that would be glorious. But also here again, you can find many of the original Milk presets ported to WebGL. And I didn't even have a finger on it. So, why am I here? Why am I talking to you? Because I think you are missing a point when you look at fractal images. Most of them are rendered for many minutes, and I think it's a waste. You can have instantaneous feedback if you know how to do it right, and it's not in every property the same, but you can come very far with very little. So this is a progressive image-based approach to fractal rendering. In every animation frame, I'm adding the previous frame, adding one bit to the color depth, and afterwards I apply bump map filter. And it's really simple. This whole shader program is maybe two lines for the feedback and another 5 lines for the composer. So the Julia fractal was a single complex number operation on the frame. This funny little tree is not even using complex number calculus, but it is composed of 3 smaller copies of itself. You see the branches on the left and the right. These are smaller copies of the whole thing, and also the main branch after the first junction. it's also a slightly smaller copy of the original frame. The same thing with 4 copies can lead to almost 3D impression. Actually, it's really not 3D in this case. It's just playing with the perspective and 4 copies of the same fractal. So I said it before, I can't support every type of fractal. These are very special types of fractals that have the property to converge. The Mandelbrot definition is another one. This is a point belongs to the fractal if it converges or if not. It's one level up, and I can't support this level. So here it says the Mandelbrot set is a set of values of C in a complex plane for which the orbit of 0 on the duration of the complex quadratic polynomial remains bounded. So what I'm not doing is iterate over and over again and then look if it's in the limit or not, but I just don't care. I just calculate on and on and on, and even if it reaches the point where it converged, I do it still because whatever. So there will be no 3D fractals like the Mandelbrot. You're supposed to laugh now, because this is something to eat. I play jokes myself. I call it a Flappy Bird. I don't know if it's really a Flappy Bird, but it is also really old. I did this on the last day of the JS1K compo last year, and actually I've did this before with. How old it is, but I think it was 2008 or 2009 when I released this funny little dirty guy. So holding this talk under the title Abstract Pixels because I don't see pixels only as RGB on the screen. I see pixels as an array of vectors. You can store anything in it if you want. You can use the RGB to transform, but you are not bounded to it to display it directly in the same form. You can color each channel separately and stack them on top of each other. You can use many color channels. And in the end, you can totally diminish this color thing and say, why not is this value a property of an agent in a sense that it can walk around and explore the world. It can have a position, it can have a velocity as a funny little pixel that moves around. Or you can think of simulations. Yes, I can read my bulletins. Cells in a forest fire epidemic simulation. Let's say you have a forest and you use a regular grid and you say, there are that many trees and it's so hot and the wind comes from that direction and the neighbor is burning. Oh my god. And as it will take on. Also, you can simulate how information travels in a flat area. And last but not least, and this is where my talk continues, is concentration of chemical substances. John von Neumann proposed a way to simulate or to an explanation for the patterns on leopard skin and zebras. And I will come back later to this. So first, cellular automatons. Cellular automatons is that what I said before with the fire simulation. And you have very simple programs that are be executed on a single pixel for every pixel on the screen, and the new state of the pixel is defined by the state that the pixel had before, and also the state of the neighbors. The most famous, of course, is the Game of Life by John Conway. Sorry, it loads the time. And this one is executed here on a 2 megapixel texture. If you would do this on a CPU side, you could wait for every frame up to several seconds, and this one runs just fluently. I've also programmed the magnifying lens in this one. Another quite funny one to explore, to find in the first place, is a rock, paper, scissors simulation. So you have red, green, blue, and don't want to lie. Blue beats green, and red beats blue, and green beats red again. This is the only rule, and strange things are happening then. It's not the only rule. I'm also doing another thing. Each color patch is floating in the direction where its gradient points. So when there's a green color patch, and it will just continue to grow in the area where it's not present before. So I talked before, blur is very important. Blur is very important for this gradient definition and for some other effects. And also blur is surprisingly cheap on the GPU. You can have a texture that in the foreground is the one from the feedback loop, and the stack of the different levels of blur in the background are calculated for every frame. And the trick is that you don't calculate the operation for every pixel of the, in this case, 7 by 7 matrix convolution, but you can separate this into 2 passes, one horizontal, one vertical. Each one has only 7 lookups, and then if you go down the ladder, you can reduce the resolution and save even more. I've also tried my hand at integral images in summed area tables. These are images where you add the value of a pixel to the predecessor for every pixel, so that you can do arbitrary lookups for different rectangles and have the average from a box. But the build-up process of the summed area tables was not feasible enough for me to do in WebGL. So I introduced the works by Alan Turing before, and the reaction diffusion stuff for the natural looking patterns for like zebra stripes or leopard dogs and whatsoever. And the algorithm behind it is simply the difference model of two different blur levels. I don't want to go into detail. These are external links, and you can look it up afterwards. The whole presentation will be online. So you have a ground signal, and then you take the blurred version of it and look for the difference. You could say the rich get richer and the poor get poorer, and then you can blur this again and this again. And yes. This one was pretty neat. It was made by Frederick van Hoot. At least he wrote a blog article about it. Actually, it was Jonathan McCabe who introduced this simulation code in a paper, and yes, I tried my hand at it. And this is how far I came. So I have to hurry. I have so much nice things to show. So the whole WebGL program of this simulation, just let it run for a while and go directly to the source code and show you what makes the scene up. There are different shader programs, I said, mainly the advanced shader program and the composite shader program. In this case, the composite shader program is a one-liner. It simply takes the red channel and maps it to white. So the whole thing happens in the red channel in the advanced shader. And you can see it in these three lines. That's all. But it really gives a nice zebra pattern, I think. The warp on this one, so the flow and the motion is defined by simple sine and cosine values that vary over time. If you want to believe me, and I can show you if you want. It's really real time and it's all interactive. So, I don't know who of you has ever zoomed into a zebra's fur before. Some people have strange hobbies. Yes, I think it's very meditative to do. It's fun to me. Yeah, don't show this to a zebra. Of course, when they are partial differential equations at work. They are, of course, more sinister for them. This rotation in the background is actually from a predator-prey simulation model. It's the Lotka-Volterra model. You can say the x-axis is the prey population, and the y-axis is the predator population. And when it's exactly the opposite. The y-axis. I always confuse this. Let's say when there are no predators but a lot of prey, the prey will continue to grow, and then the ratio. Oh, I have too much different other type. Yes, I'm drifting away. I knew that it would happen. she's a giraffe pattern. It takes only a few seconds. Maybe. Okay, good. Just have a look later on. So, I was invited to talk about my programming at the FMX conference in Stuttgart 2013, and I think it was due to this example in particular. This one was where I have originally gained a lot of fame. And it's really simple again. There's only one color channel used. It's the red one, not so obviously because it's recolored. And I could go through the code with you and explain every code line, but I think it's even self-explaining. I've commented the code. I endorse you to download it and check it out. So noise is not so important. You can generate your own noise from procedures. I have pre-calculated some noise textures to use it first. The simplex noise is out there, but I think it's still not so real time as I would like to have it. You can do many funny things with only some noise. I haven't even started with the fluid simulations and the particles. I have to go quickly through this. 5 minutes. I think we must skip the question and answering part now. It's not so much fun to explain it, it's really simple, because even I can look at it and think, I don't know what. But the code is there, it's open, it's wild, go run for it. All I do is very minimal effects. Bump mapping, complex numbers, and stuff like that. So I showed you the initial ray tracing approach to this panorama photos. I haven't started there. I started with ray tracing of force fields, and this is one that's very simple. Typical shader guy looks at it and says, "Where's the lights and where's all the effects?" And that was not my point. All I was trying to show you was there's again not more geometry used than two triangles. So the rest is ray traced, and it's fast as hell. There are many operations like the polar coordinate transformation, and it is astonishingly cheap to use. Especially when you have texture that are actually tiles. All these simulations are flowing over the edge and you've seen this idea before as a fractal feedback loop. In this case, the same math to the application of the four roots in the complex number plane is used to deform the original or traveling wavefront demo. And when you combine the polar coordinates and the complex numbers, you can have two poles, bipolar. Actually, these last two demos pointed to external tools which include shader editors on the web, ready for your amusement. Yeah, this one is GLSL from GLSL Sandbox. Many people contribute to it. You can directly jump and edit the shader code. Polar complex numbers can produce black holes. Have you ever pointed with a black hole through the Earth? It's not physically correct. So, but when I'm talking about projection, I also mean you can have a scene, like many particles, let's say 500,000 particles, and you paint them to a texture. Then you have a density map of the particles, and you can use the density and the gradients in the density to update the particles' positions again. This is why I hurried so much and worried that my time is too short, because this is only the start with the particles. And I also did fluid simulations, so shock and awe. During fluid simulation, this one was shown on many blogs, including the Chrome experiments and the official Chrome blog. It brought me many followers. So 10 minutes to go. It must be enough for the particle soup and the other particle experiments. Yes, I'm sorry. Okay. I said you can use the pixels in a texture program to represent other things than RGB values. This block of 2 million particles is stored in a texture and updated every frame with a pixel shader, a fragment shader program. So actually this one is not updated, but it's static. But there are really nice algorithms that are simple enough to where can I click my slides here? Okay. So I did some strange attractors in 3D with particles as well. These strange attractors are defined by one-liners for the x, y, and z component of the pixel particle positions, and they are updated every frame by a shader program, and this one is 500,000 pixels at a time. And the formula can be added around, and the integration parameters can be edited live. So we come to my successor speaker. Just want to leave this and takes a moment to get to full power in. I think we can start the question and answer time now.
Yeah, thank you, Felix. I think it was very fascinating to see all these different pictures from just so simple lines. A big applause for Felix.